our channel. Today we are going to understand the elementary continuous time signals. So जब भी हम किसी मैथमेटिकल मॉडल को डेवलप करते हैं सिग्नल मॉडलिंग के लिए, that we are having any physical system, then we model it with mathematical equations we always need to have tested. So for testing we are having certain component. So testing हम किस लिए करते हैं? First question. Testing हम करते हैं to know the behavior of a designed system. So we should know the behavior. So behavior of the system. So for testing we are having certain signals. So first of all we are taking unit step function. So unit step function के एग्जांपल्स क्या हैं? सबसे पहले क्वेश्चन ये आता है कि जब हम कार का इग्निशन करते हैं, इग्निशन की जब हम रोटेट करते हैं तो हम इंजन को क्या दे रहे होते हैं? स्टेप इनपुट टू स्टार्ट द मोटर, राइट? एंड likewise when we apply the brake, to any automobile, so that is again application of constant force. So brake to an automobile, so that is a application of constant force. So how we can represent it? We can represent that particular signal by ut. Ut is representation of unit step signal, and the value of the signal is 1 for t is greater than and equal to 0, and it is 0 when t is less than 0. So अगर हम इसको ग्राफिकली रिप्रेजेंट करते हैं, so we are having the representation like this. The signal is going to increase from the 0 and reaching towards the. Now question is, what are the component on the x-axis and the y-axis? So again there is a time and this u. So u is varying with respect to time. So this is the representation of unit step signal, and the magnitude of the signal is 1 here. And in the same way, if I'm going to represent a component of a signal u, that is a unit step, by t minus a, what is this? The value of the signal is 1 for t greater than and equal to 0 or a. So it is a, and it is 0 for t is less than a. So the representation here is that we are going to vary the component t, and here we are having u t minus a. So that is going to start the component from a. The previous values are 0, and the magnitude here we are having 1. So it starts here 1. So it means the value of ut minus a is going to start the value at a. So this is a fundamental concept when we are going to represent a unit step signal by delay or by shifting the value of the signal by a argument. Next is unit ramp signal, or we can say function. So this is second one is, so this is unit ramp function. So unit ramp function is represented by rt, and the value of this function is t for t greater than and equal to 0, and this value is 0 for t less than 0, right? So graphically we can represent it like this. This is t and this is rt, and the value of the component starts from 0, and as the t is going to increase, the r is going to increase. So this is the shape of the signal we are having. It is increasing in order. We can also give the scale to the y component and as well as to the x component also. As t is going to increase, the r is going to increase. Or we can also represent that r t is equal to t ut, because t is going to increase the value from 0, and that nature of the u is there, so it is going to represent the causality of the signal. In the coming session we are going to understand what is the meaning of causality. So the ramp function can also be obtained by applying unit step to the integrator in case of continuous time signal. So we can also find by RT is equal to the integration of ut dt. The integration of ut, as you know, is represented by this, and it is t in the interval t is greater than 0. In other words, we can write that ut is equal to the derivative of r with respect to time, or we can say the time derivative of r. The third component here is unit parabolic function. So here it is represented by p, function of time, and represented by t square by 2 for t is greater than and equal to 0, and it is 0 for t less than 0. And we can represent graphically in the parabolic form, because the function is t square by 2 and it is t, and here the variable is pt. We can give the scaling to the x component and as well as to the y component, and the shape is, because the function is in the t square form, the shape of the function is going to like this. So this is the shape of the function and we can calculate the value of p at different instant of time. Again, the ut is going to represent the causality of the signal. It means we can write that pt is equal to t square by 2 ut. In the same way, the unit parabolic function can be obtained by integrating the ramp signal, like pt is equal to the integration of rt dt is equal to integration of t dt, and that is nothing but is equal to t square by 2. So we can say the pt can be obtained by integrating the ramp signal, and we can also say that we can obtain the ramp signal by taking the time derivative of p. So this is all about the parabolic function representation. Next is fourth one. Fourth one is impulse function. Impulse function. The impulse function occupies an important place into the signal analysis, as it is represented by integration of the delta, which is a function of time with respect to time, and the limit from minus infinity to infinity, that is equal to 1. And we can also represent it by delta t is equal to 0 for t is not equal to 0. The graphical representation of this signal is, we are having the component on the x axis, that is xt, and on the x axis we are having time, and the magnitude is 1 by delta and with the delta instant of time. So this is the representation of rectangular pulse function. We can say impulse, that is the impulse function has 0 amplitude everywhere except at t is equal to 0. At t is equal to 0, the amplitude is infinity, such that the area under the curve is equivalent to 1. Note that the area under the rectangular pulse is equal to unity. The rectangular function can be represented in this form, and we can represent it like xt is equal to 1 by delta ut minus u t minus delta. So that is the representation of xt. Now the graphical representation of this mathematical representation is, we can write that ut can be represented in this way. Say this is 1, and ut minus delta, here it is represented by this graph. Here it is going to start from delta, the amplitude is again 1 here. If we subtract these two components, so we'll have our resultant function, which is what? Which is ut minus ut minus delta. So if I'm going to subtract this from this, then we are having this section left, so we can have this area left. Here this is 1 and here it is delta. So this is this functions, and we can get the rectangular function. So this is rectangular function. So if we are having this representation here, so we have to represent here the delta t. So we can have the delta t by putting the limit that delta t tends to 0 when xt is there as a function. So xt is nothing but this one. So we can have the limit delta t tends to 0, that is 1 by delta ut minus ut minus delta. So this is the delta function we are having. The delayed unit of the impulse function now we are going to define by integration of delta, which is delayed by a, is equal to 1. So that varies from minus infinity to infinity for t is equal to a, and the representation is like this: the delta t minus a, the value of this function is 0 for all t not equal to a, right? So if I'm going to represent a function of delayed by a, it is going to represent by the graphical representation. Here if I'm having the 0 and here if I'm having the a, then there is a spike of, if it is a unit impulse, then the amplitude is 1. Otherwise we can represent by del t minus a. So on the x-axis we are having time as a variable, and here we are having a single spike if I'm going to represent a delayed impulse signal. So hope you like and understand the concept. So please like and share the channel.